Okay, hello MathCounts friends. Today we're going to do this year's chapter target round. So they released the chapter tests a day or two ago, and we did the sprint round yesterday. And so today we're going to move on to the target round. So I am just going to go over the four problems that a lot of our top students got wrong. So let's start with this one here. This was problem number 5. And it says if f of x is 3x minus 27, what is the greatest real number x for which f of x squared is equal to f of x quantity squared? So what we can do is just plug in to these expressions and set them equal to each other. So if we have f of x squared, that means we plug in x squared for what is x here. So f of x squared is going to be 3 times x squared minus 27. And we're going to set that equal to the f of x quantity squared. So f of x we have here is just 3x minus 27. And then we square that. And now it's just a matter of doing a bunch of algebra. So I'm going to leave this part alone over here. This is just going to be 3x squared minus 27. And then over here I'm going to expand this out. So I'm going to have 9x squared and then minus, let's see, we've got 27 times 3 times 3x. I'm just going to write it out. I'm just going to write it as 6 times 27 times x rather than worrying about multiplying it for now. And then you get plus 27 squared. 27 squared here. All right, great. So first, the next thing we could do is subtract or bring this over to this side so that we have just a quadratic equal to 0. So let's do that. So we're going to have to subtract 3x squared from this side. That's going to change this into a 6x squared. And then we're going to add 27. So what does that give us? That gives us 0 equals 6x squared minus 6 times 27x plus, I guess this is now going to be 27 times 28. Yeah, because we had 27 times 27 and then we added another 27, so it's 27 times 28. So I guess all these are divisible by 6, so we could divide this by 6. So we still have 0 over here. We're going to have x squared minus 27x. Oh, I'm glad that I didn't multiply that out because now I just get to cancel it. And then plus, I guess if I divide this by 6, I can divide the 3 here. So that's just going to give me 2 times 14. Because I divide the 2 here to give me 14, and I divide the 3 here. Oh wait, what did I say? This is divide by 3 here is 9. So 9 times 14. Is that right? Let's do 9 times 14. Okay, great. Which is, I guess I can calculate that. It's 126. All right, so now I've just got a quadratic equation, and they want to know the greatest real number x. So normally in the quadratic equation, you can find both of the roots by doing minus b plus and minus the square root, blah, blah, blah. But since they want to know the greatest real number, we're just going to do plus instead of plus and minus. So plus square root of b squared minus 4ac over 2a. And here's where you pull out your calculator and you just plug it into quadratic formula. So let's do that. I've got Python here. And we can do minus b, that's minus a negative 27, so that's 27, and then plus the square root, I'm using NumPy, so np.square root, square root of b squared, in Python I do b times 2 like that for b squared, minus 4, oh wait, I gotta do b, what is b? b is minus 27, so that's just gonna be 27 squared. Minus 4ac, so 4a is 1, I don't need that, and then c is 126, so 4 times 126. And then I'm going to divide that whole thing, don't forget the parentheses here, divide that whole thing by 2a, so 2 times a is just 1, so actually I just divide by 2, I guess. And we hit enter, and we get 21, so that was the answer to that one. For some reason, which is very strange. The answer key says 21 blocks, and I don't know what blocks has anything to do with this problem. But anyway, that was what it says. So there you go. All right, I hope you enjoyed that. We'll move on to the next one. Again, don't forget to pause the video when you see the problem and try to work it out on your own before you look at the solution, if possible. So here we have a problem about money. It says in MathCountia, the currency denominations are $1, $9, $81, $729. So they're using like a base 9 number system, I guess. It says if Coda has 500 pieces of MathCountia currency whose total value exceeds $10,000, what is the least possible total value of Coda's currency? So if we wanted to try to have $10,000 in as few pieces of currency as possible, I guess we would just kind of convert 10,000 into base 9, because this is 9 to the 0, 9 to the 1, 9 squared, 9 to the third power. But that's not really what we're trying to do. We're trying to get 500 pieces of currency. But maybe it's a good place to start. So let's just start with that and see where it takes us. So I'm going to bring Python in again so that I can do a little bit of calculations here. So let's take our $10,000 that we have, and let's divide it by 729, which is the biggest piece of currency we have. That tells us it's 13 and some change. So we could have 13, for example, we could have 13 $729 bills, right? So let's do that. Let's say we've got 13 of the $729 bills. And now we have some money left over. How much money do we have left over? Well, we have 10,000 minus 13 times 729. We have $523 dollars left. So we could put that all as $1 bills, and that would be too many pieces of currency, right? Because we need exactly 500 pieces of currency. So maybe what we need to do is put some of those as $9 bills, right? So every time we change, if we use 13 $729 bills and then we use 523 $1 bills, we'll have exactly $10,000, but we'll have too many pieces of currency. So maybe what we need to do is trade in 9 of our $1 bills for a $9 bill, right? And that will keep the same amount of money, exactly 10,000, but it'll reduce the number of pieces of currency that we have. And in fact, it'll reduce it by 8 every time we do that. So right now we have 524 pieces of currency. No, we don't. We have 13 plus 523, actually. We have 13 plus 523, which is 536. So we could do that, let's see. I guess we could do that. We could trade in 9 ones for a 9. If we did it 4 times, we'd have 502 pieces of currency, which is still too much. So what if we do it 5 times? Okay, so let's try that and see how it goes. So let's say we have 5 $9 bills, right? And then what does that leave us? Let's see. So we've got 500 minus 13 minus 5. That will tell us how many $1 bills we need. So that's 482. So we have 482 $1 bills plus 5 $9 bills plus 13 $729 bills. Oops, 729. And that gives us 10,004. And that is actually the answer. So that is the lowest amount of money we could have with exactly 500 pieces of currency. So it's $10,004. I guess we didn't even have to deal with the $81 bills, and I think if we would have put an $81 bill, we wouldn't have had enough. We would have had to use a lot of. Well, we wouldn't have been able to get up to 500 pieces, right? Because if we had done our 10,000 minus 13,729 minus an $81 bill, that would have only left us with 442 $1 bills to get up to 10,000. Well, yeah, so then, or let's see. So 442 plus 13 of the ones and one of the others. That would be only 456 pieces of currency. And if we added another 44 pieces of currency to get up to 500, we would have ended up at 10,044 or something like that in terms of dollar bills. When we wanted to get the lowest possible, so the $81 bill really didn't help us. It's really, this is the best we can do. All right, great. So that was the answer to that one. Let's move on to the next one. So again, that one was problem 6. Let's move on to the next one. This one is problem 7. Problem 7. It says a container holding 9 milliliters of solution. A lot of you guys got this one right, so this one wasn't too hard. A container holding 9 milliliters of solution is 50% syrup by volume. After adding some pure water to make the solution 30% syrup by volume, how many milliliters of solution are in the container? So the way that I did this was I said, okay, how much syrup is in the original solution? If half of this 9 milliliter solution is syrup, that means I've got 4.5 milliliters of syrup, and that's going to stay true even as I add water. So if I take that 4.5 milliliters of syrup and I divide by the total volume, which is what we're looking for, it says how many milliliters of solution are in the container at the end. Let's call that X because that's what we're looking for. If I take that 4.5 milliliters of syrup and divide by the total number of milliliters at the end, that's going to give me 3/10, or 30% is 3/10. And so this one's not too bad. You can just cross multiply here. 45 times 10, or sorry, 4.5 times 10 is 45. And we can set that equal to the multiplication on the other direction, which is 3x. And so this one just says that x equals 15. So if you want, you can double check that. You can, but there's different ways to do this. But, for example, you could say, okay, that 15 is going to be 6 additional milliliters of water, which puts us up, it's 4.5 divided by the original 9 plus 6 additional, it's going to be 30% there. So no, did I do that wrong? I did that wrong. Anyway, let's see, what did I do? How many milliliters of solution? So yeah, we're adding an additional 6, and 4.5 divided by 15. Yeah, that is 0.3. Yeah, so that's correct. Okay. Let's go on to number 8. So this one is number 8, and this one was really hard. So let's take a look at this one. So it says Shrinky the Frog wants to hop on some lily pads in the 5x5 grid shown. Shrinky may start at any lily pad. Okay, so it shows Shrinky here, but he can start wherever he wants, or she, I don't know. And each hop is a straight line to the center of another lily pad. However, Shrinky gets tired as she jumps. Oh, there you go. Shrinky is a she. And so each hop after the first must be shorter than the previous hop. Furthermore, Shrinky is not allowed to visit a lily pad more than once. One possible sequence of hops is shown. Okay, so Shrinky could jump from here over to here, and then to here, which is a shorter hop, and then from here is a shorter hop, and another shorter hop, and another shorter hop. That would give her 6 hops. What is the largest number of lily pads Shrinky could visit using a sequence of hops? Okay, so feel free to pause. I'm going to go into the solution now. All right, so the first thing to think about is if you want Shrinky to have lots of hops, you're going to have lots of different distances. And so maybe what we should do is just think about all the possible distances that Shrinky could hop, from the shortest up to the very longest. And of course, to compute the distances, you effectively are using the Pythagorean theorem, right? A squared plus b squared equals c squared, right? Because you go over a certain number of lily pads and down a certain number of lily pads, or up, whatever it might be. And so, for example, if you go over 3 and down 1, that's 3 squared is 9, plus 1 squared is 10. It's the square root of 10 would be that distance. So maybe what we could do is just make a list of all the possible c squareds. And a nice way to do it would be to say, okay, I'm going to be able to get all, if I start at a corner, I'll be able to go all those different distances, right? Including the very longest distance, which is from corner to corner. So what is that? Maybe we'll start with that one. If we go all the way, I'm going to pick a color that contrast. I'm going to just draw with black here. Let's see how that works if I just draw with black right on these lily pads. So starting from here, if you go over 4 and down 4, that's 16 plus 16, that's going to be 32. Is going to be c squared, right? That's going to be c squared. And what if I go over 4 and down 3? That'll be 16 plus 9, right? Yeah, so that's our 3, 4, 5 triangle. That gives us 25 for c squared. If I go, let's see, I could just go over 1. That would give me 1. I could go over 2. That would give me 4. And then 9, and then 16. And then I could also just go down 1, but that's going to be the same distance. I want to just make a list of all the unique distances. So actually, I think I'm going to cancel out all these ones down here because they're just going to be the same distance as the mirror image across the diagonal. Right? So in other words, I only need to consider, in order to get the unique distances, I only need to consider the ones up in this upper triangle here. So I'm going to get all the unique distances here. So 1 and 1 is 2, 4 and 1 is 5, 9 and 1 is 10, 4 and 4 is 8, 9 and 4 is 13, 16 and 4 is 20, and then 9 and 9 is 18. So those are all my distances. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, oops, I didn't draw this one. This is 16 and 1, that's 17. Okay, so yeah, there should be, we've got 4 here, that makes 8, plus another 3 is 11, and then 3 more down here, that's 14 distances. So let's just write that over here. We've got 14 distances. Now, you're probably running out of time by this time because there's only 6 minutes, I think, to solve these. Is it 6 or 8 minutes they give you for the target round? Anyway, you don't have a lot of time. So you might just guess that the answer is 14 because that's the total number of distances. Well, not 14 actually, because this says the largest number of lily pads that Shrinky could visit. That would include the lily pad that Shrinky starts on. So actually you could just guess that the answer is 15 because you start at 1 lily pad. If you do 1 hop, you've visited 2 lily pads, right? But if you do 14 hops, you've visited 15 lily pads. And it turns out that that's actually the answer. But we haven't really proven it yet. All we've done is figured out how many different distances there are. It might be that when you start hopping these things, you'll realize that, oh, there's actually no way to do all those hops because you get stuck in a corner where there's no way to connect it. But let's see if we can just show it anyway here. So let's say that, now if we want to do all those distances, one of the distances is going to have to be from corner to corner. In fact, it's going to have to be the first hop because the first hop has to be the biggest. So that means Shrinky's going to have to start on one of the 4 corners. And it doesn't matter which one we pick because it's a symmetrical thing. So let's just say that she starts here. That's number 1. Then number 2 is going to have to be down here on the other corner. And number 3 is going to have to either be here or here. Let's just pick this one. I don't think it matters. And then number 4 is going to have to be the next biggest distance, right? So we said the biggest distance was 32. The next biggest distance was 25. The next biggest distance is 20, which means you go over 4 and down 2. So from here, if we go over 4 and down 2, we'll end up here. That's the 4th spot. And then the 5th one is going to have to be a 3 and a 2 from there. Is that right? Yeah, a 3 and a 3, is it? It's a 3 and a 3. Yeah, a 3 and a 3. So from here, if you go a 3 and a 3, you have to go up 3 and over 3. So you'd end up here. So we'll circle that one. I'm just going to maybe circle them to say that I've been there. Okay, and then from there, you've got to go over 1 and down 4, right? Because the next biggest is this 17 here. So you go over 1 and down 4. You can either go here or here. I think it's probably safer to go here so you have a little more options. So that gets you there. Now the next hop is going to have to be this one. Let's see, are we on the 9 now? What are we on? We did 1 and 4. That was the 17. So now we have to do the 16, which is straight up 4. So that's going to get us up to here. And the next one is going to be, let's see, the next biggest one is going to be 13. Is that right? So that's going to have to be 3 and 2. So 3 and 2 is going to put us here. Because if we go this way, we'll end up in a spot we've already hopped on. So that's going to put us here. And then after that, we did the 13. The next biggest one is going to be the 10, which is a 3 by 1. So here we have to go 3 by 1. If we go up 3 and over 1, that's not good. If we go this way, yeah, this one's good. Here we can go to there. And then the next one is a 9, which is straight over 3. So we could go, if we went over here, that's one we've already visited. So let's go down 3 to here. And so, oh wait, where was I here? No, I started at the wrong place. I should have numbered these. Now I can't remember where I was. Let's see, so we were here. Yeah, we were here, and then we went to here, but I'm not sure that's the best place to go. Oh, whoops. Oopsies, that's not what I wanted to do. Let me undo that. Sorry about that. Okay, yeah, so I went over 3 and up 1. I could have gone over 3 and down 1. I think that is actually gonna end up being better, turns out. So, and then now I have to go, because from here, if I went straight 3, I would end up here. Yeah, so let's go down here, and then we gotta go 3, which is this 9 one here, ends up here. And then after 9, we have to do 5, which is, or no, 8. 8 is over 2, and it's 2 and 2. So from 10, if we go 2 and 2, we'll go to this one. And then from this one, we need to do the 5, which is 2 and 1. So that can put us up here. That's our, and then the 4 is over 2. So let's go down to here. And then we have to do the 2, which is 1 and 1. So we can go either here or here. It doesn't really matter, I guess. Either one has a neighbor. So we could go here, and then we need to do one more jump, which would put us here. So if you count up all the ones we've jumped on, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which we knew it was going to be because we knew that we did 14 jumps. So that was the answer to that one. All right, great. I hope you guys all enjoyed that and learned something. And I'm going to do the team round 1 as well soon. So I'll see you guys in the next video.